Hi there! What I have here is a replica of the Jupiter Ace computer. Now usually I feature projects that I design myself on this channel, but occasionally I like to just go build something cool that I found online. And this here I found in a Hackaday article. It's on hackaday.io that was called Recreating the Jupiter Ace. Now the Jupiter Ace was a computer from the 80s, maybe 82, 83 or so. It was a contemporary to the ZX Spectrum, the ZX81, ZX80, machines like that. But what made the Jupiter Ace unique is that rather than having BASIC in ROM and booting to a BASIC environment, it had the programming language Forth. So I've been on a bit of a kick lately with some Forth related videos, and that's why I decided to pursue this. Forth was a language that I did learn in my youth. I learned it right after learning BASIC because I felt like it gave me the power and structure that, BASIC did not. But then I quickly moved into Turbo Pascal, which was kind of conquering the DOS space at the time, and I became a Pascal programmer. Then eventually became a C programmer and a Python programmer and a Go programmer. But Forth was in there, near the very beginning of my programming experience. So the author of this project, he published the KiCad files. So I went and I downloaded his KiCad files, I exported the Gerbers, I had JLC make the PC boards, and I soldered it up and built myself a Jupiter Ace. But it didn't work. There were a couple of things that I had to fix. So we'll talk about those difficulties that I ran into, and then, just because I do like designing my own things, I will show you a RAM expansion module that I designed. I will show you a Raspberry Pi supervisor module that I designed. And of course, you know it, a speech synthesizer based on the SPO256 that also I designed. So we'll hook all these modules up to this Jupiter Ace and make it do a few other things. Okay, here is the Jupiter Ace circuit board. So down here we've got the keyboard. It's got the 26 letters, the 10 numbers, and enter, space, and shift and control. Now if you build one of these, you'll want to make yourself a keyboard chart here, because a bunch of these will have symbols and stuff on them. So like the delete is actually shift 0 is that's your backspace character, or shift 1 is your delete line. There's caps lock. Some of these have graphic symbols that you can type graphic characters. The punctuation, some of them are in kind of weird spots, and you'll do that with the control key, which is actually, I believe it's the symbol shift. So it's a little bit, the layout on this keyboard here is a little bit different, because it's got the shift and the control shift over here, whereas this one I printed online had the control shift over there. So over here we've got the Zilog Z80 CPU. Over here is the ROM. I actually used a WinBond 27C512, an erasable, electronically programmable, the double EEPROM. Then we've got a total of 3 static RAM chips. This one here has your program memory and some other stuff. This one here is your video RAM. And this one here is your character generator RAM. Now the original Jupiter Ace design used 2114 RAM chips, which are a 4-bit chip. And the author of this project changed that to use these 6116s, which are a little bit more readily available, and they are 8-bit RAM chips. So you've got 1K here, 768 of that is your program RAM, then you've got 1K here for the video and the pad, and then another 1K down here for the character generator RAM. You've got your video out here on the side. It does have an onboard speaker. I use this little round speaker that I got from Mauser for another project. Over here would be your voltage regulator. So I used a Pololu step up, step down regulator because it actually will regulate all the way down to 5 volts, even a little bit below 5 volts, and still give you the 5 volt output. So it will either step up or step down as appropriate. Normally you would have like a 1/8 inch jack, like an audio jack over here for the power in. So I don't really like using, something that looks like a speaker jack for power. I like using barrel connectors, so I actually stuck a barrel connector on there and then wired it to the jack positions. Lots of resistors in here, so there's a set of them there, and there. And they do things in what seems to be kind of a strange way, possibly to just save money on chip count and avoid a few bus transceivers. They would put data lines through a resistor and then multiplex that with something else, so that the something else would override the data lines, but when that went high impedance, and the data lines could take over through the resistor. It's a little bit funky, but it seems to work just fine. And then the rest of this is all just logic ICs, so 74 LS logic. Lots of 367s to do kind of bus transceiver type duties. So this thing doesn't have a graphics controller in it. It's all done using various counters and other logic over here that sequences through the video RAM and then takes the video RAM through the character set RAM and uses it to generate pixels. So that all happens kind of over here in this section. Then you've got your expansion connector out the back. Okay, let's go ahead and turn it on. And we've got kind of this nasty white background. I can unplug the monitor, plug it back in, and it's still there. What I found, I hit return a bunch of times, and now we unplug it and plug it back in. Now we at least have a picture where we can see some characters. So we see some white on lighter white or darker white. And I think what this comes down to, I've played with this a bit, it's this IC over here, this 555 timer IC, along with its associated 68 and 56 ohm resistors. And I think what this is trying to do is set the back porch values for the composite signal. So that's a value that goes out, maybe it's around the retrace interval, that sends out a certain voltage to the monitor and lets it know kind of what voltage to expect and how to set the gray levels. Something about it is not working right. This maybe it's designed for PAL, whereas this is NTSC. I don't know. I'm not a composite video expert. But what I did find out is if I just take that 555 timer and remove it, there we go. Look at that. Usable video. IC removed, and we just saved like 39 cents. Okay, so great. Now we have something that is that we can use. 1, 2, 3. Then a dot. Everything's working, but we do have, there's this like weird symbol over there next to the cursor. What's up with that? You know, you can see it's separate from the cursor. What is that? I've got a reset here. I'll reset it. Now the weird symbol still there, but it's something else. Once again, different weird symbol. And what this is pointing to is a problem with the character generator. This is actually a null. This is code 0. So if I do a 0, let's see if this will actually work. Emit. We can probably get another one. Yeah, see, there he is. There's this 0. So this is the value. It sits right next to where you're typing in, and it has that null character. And that null character should be blank, but on reboot, the character generator RAM is getting set with some kind of weird random value in there. And I found the character generator in general seems to have problems. Let me try something else. I'm going to get a little bit ahead of the thing here and load a program into this. Just bear with me a second. I'll explain what this is later. So let me explain what I just did here. So this is a program that came out of the Jupiter Ace manual, and that program is for setting characters in the character generator RAM. And it tries to set the character to this thing that it calls a train symbol. Train is that symbol there, and I set it to the first 10. So the Jupiter is kind of cool in that the character generator, the thing that turns values in video RAM into pixels on screen, it's in normal RAM, and you can just write it. And you can redefine any character to look like anything else. So this tried to define characters 1 through 10 to be this train symbol. And it did that. So characters 1 through 10, they did pop up and change like they should have. But it also screwed up a bunch of other characters. So like the T got messed up, and I never did anything with the T, and the N is messed up there. the spaces all turned into, something with a dot stuck in them. Looking up in here, we can see the 1 is messed up, the colon is messed up, M is not right, T is not right. So clearly something is going wrong with that character generator RAM. And I'm going to try to diagnose that and see what it is. Okay, so I tried a couple things to fix the character generator RAM corruption issue. The first thing I tried was switching the RAM chips, and I had some here. The ones I had were 400 nanosecond. I got some 200 nanosecond and some 55 nanosecond, both from JDR Micro Devices on eBay. And I replaced the video RAM, the character generator RAM. That didn't really that didn't improve it. It behaved differently. But it did not behave correctly. Then I went and I replaced any HCT chips with LS chips like were in the schematic. So my thought there was that, we've got these resistors where we're sharing data bus, or we're sharing the address bus between data and address based on whether you're reading and writing the video RAM or you're, accessing the character RAM. There's all this weird bus sharing going on. I thought, maybe the logic family is the issue there. And, the HCT levels being a little bit different than the LS levels and drive capability and such. But that didn't make any difference. Then I noticed that this thing it's almost completely devoid of bypass capacitors. So for my last shot in the dark, I stuck bypass capacitors around all of the ICs that were around here in the video RAM and character generator RAM area, including the 2 static RAM chips. But that also yielded no change in behavior. Okay, I think I tracked down the problem to here. This is the character set RAM, and these are the address lines that go into it. So for what we're seeing, for different cells to get corrupted must mean that these addresses have the wrong values on them when this write pulse comes in. So if we look at this write pulse, we follow it around, it comes over here, it comes up to some logic over here that's taking the write from the CPU, merging it with the MREC line. It's got a weird little resistor thing here, don't worry about that. But anyway, write comes from there. But now if we look at the address lines, they're coming from these 74 LS367s up here. And going up a little bit more, they're getting triggered by this XOR gate, which is coming over here from this other gate. Now, if we think about the timing of this, the write enable gets triggered off of this gate. Now, about 20 nanoseconds later, a pulse is going to come out of this gate. And about another 20 nanoseconds later, a pulse is going to come out of this gate. And then about 20 more nanoseconds later, this guy is going to let the address lines through. So that means that this write is getting triggered 60 nanoseconds before the address bits are set out here in the address lines. So, maybe for some RAM chips, that's all right. The Jupiter Ace was originally designed with a pair of 2114 4-bit RAM chips. The guy who designed this project replaced it with a single HT6116 or, HM6116. That's an 8-bit RAM chip. He made that substitution and maybe he had a RAM that worked, but the ones that I have are not at all liking that the write is started 60 nanoseconds before the address bits are there. What I did is I made a very simple change to this once I figured out what was wrong. And you'll have to forgive me because I'm not very efficient with KiCad here yet. So let me go in here and I'll show what I did. And just to jam my stuff into the space, I'm going to kind of overlap some symbols here, but you'll kind of get the picture of what I did. So the guy who designed the project, he added this inverter here to do the chip enables. But this 74LS04, it has 5 free gates on it. So what I did is I took 3 of those gates and I hooked them together. And then I took and I grabbed this line over here. And I ran it all the way down to there. So now what we've got is we've got this write enable, and it goes through 4 inverters. So you go through 4 inverters, you're going to get back exactly the same thing that you started out with because every pair of inverters, they sort of cancel out.
But this inverter is going to add 20 nanoseconds, another 20. Now we're up to 40 nanoseconds, now we're up to 60, now we're up to 80. So we're going to delay that write pulse by 80 nanoseconds. Now what we will do is we will get rid of the old write enable wire. That's that one. I will come in here and I will take this. Let me just clean this out as well. So now what we've got, instead of the write enabled coming off of there, we've got this write enabled delayed approximately 80 nanoseconds later. And by my thinking here, that will make sure that these address bits are set about 20 nanoseconds before the write pulse ends up hitting the RAM over here. So what I did is I went over to the board and I just hacked that modification into there on the back side of the board, just cut a trace, and then wired all these other ones together.
Okay, I've powered up, and as you can see, no weird symbol next to the cursor. So, and I can reboot it many times, and each time that thing that used to have that weird symbol is looking normal. I can do a VList. It looks like VList is working fine. And let me go run my character set test program again. So as you can see, as we should have, we changed the first 11 or so characters to the train symbol, including that little null that is next to the cursor. But nothing else got corrupted this time. All of the rest of the characters are fine. So I would say this pretty much fixed the problem this time. Now let me show you a game. This one is called Tut Tut. I've already loaded it into memory, so we can just go ahead and run it. And the weird characters are actually done on purpose. That's part of the font that they chose to use. So one of the reasons why it's important to get the character set generator working properly. Otherwise, this would be all messed up. So let's go ahead and let's try to play. And the interesting thing is this is all done using character set graphics, which is pretty cool. So I'm the little archaeologist over there, and I'm running away from all these mummies. And I have a limited amount of air. I'm not going to make it on this one, but I have to collect these keys, so I've managed to collect that key. Let's see if we can get down here. I don't have to get all the gems, but I do have to get all the keys. So I've got the 4 key. Let's go over here and get the 1 key. And once we have a key, we can move a block out of the way. Let me go grab that gem. So there we are. I made it through that level. The levels do get progressively harder. Now let's try another one called Moonbug. Press A key to play. Let's do... Yeah, like I say, there's no easy levels, so let's start with difficult. And let's start with slow. See, I can't even make that one. It happened so fast. There, I made it. Woo! Whoa! Look at that. It didn't get me when those meteors hit me. Whoops. Game over. Okay, let's take a look at some of the boards I designed. So these are all designed to plug into the back of the Jupiter Ace. So you can plug it in here. Kind of plugs in like that, and then you get a piggyback out the back so you can plug another board in if you want. That seems to be the way that the Ace would have done this, and the ZX Spectrum, and other machines of that era. So to do this, this connector is a little bit weird. Most of your edge card connectors will be closed on the ends. So what I did is I took a normal edge card connector and my hacksaw blade and just hacksawed on through it, and the other side hacksawed on through it. and then you end up with one that is open on the ends. And then you want a key, because this is keyed, you know, to match it so that you don't get it off by one. I took a couple pieces of bare wire, stuck them in there, and just put some solder on it. So that makes a good key, lines everything up right. Then on the back side, I made this little coupler connector, and you take and you squeeze the pins that came from the card edge connector together, and you can solder them kind of to the main PC board as well as to this coupler PC board. Now I realized after making these that I should have flipped and put all the components on the back side rather than the front side. If you look at like a ZX81 16K RAM module or something, you'll notice that it's in a plastic case, and the front of the case comes down kind of flat against the PC board. So I'm not sure I could really put these in a case unless I take and I flip all those components to the back side. So I may respin these boards to do that. So this first board here is a RAM expansion. The Jupiter Ace only has, I think, like 768 bytes of RAM for user programs, which is not very much. But you can add easily an additional 48K into 48K of unaddressed memory space. So what I have in here is I have a decent size RAM. I think I used an AS6E 4008. And then I have a GAL22 V10, my programmable logic device of choice that handles all the addressing. So this is actually quite a large RAM chip. We only need 48K of it. But you can implement various paging schemes. So inside of my PLD, I actually have room, if I want to, I could page that 48K in 4 pages by using a couple of data bits attached to a port. I haven't actually done the paging yet because I see absolutely no need to have more than 48K of RAM. So right now I'm just using this as a straight RAM board. The jumper up here is an enable or disable from the RAM board. Now my second board here is this one here, and this is a Raspberry Pi bus supervisor. So I have built bus supervisors like this for many of the retro computing projects I've done. I think the first one I did was for the RC 2014, and what it is, this is a Raspberry Pi 0W plugged in there. Kind of sits in upside down. And what it does is allow you, by using the bus hold line on the connector, to seize control of the all of the peripherals and the memory from the CPU. So you can put the CPU into a bus hold state. It will acknowledge that with a bus ACK, and then you can go around and you can do stuff with memory. So I've got some transceivers and some latches here that the Raspberry Pi will use to set the address and the data, and it can either read memory or write memory while the CPU is in that hold state. And you can use that to do all kinds of interesting tricks. Like, one very simple thing to do is you can load a tape file into memory, and rather than playing it through the tape interface, you just stuff the bytes directly into memory. And if you've seen me in this demo loading programs, that's how I've been loading them. Not through the tape interface, but just using the Raspberry Pi to steal access to the memory and just blasting the program directly into memory. The other thing you can do with it is, since the keyboard buffer, the input line on the screen, is actually in video memory, you can actually stuff characters into the input line through this Raspberry Pi. So this gives me like remote access capability to the Jupiter Ace. I can sit there on my Windows machine and type some characters, and this thing can stuff them down there on that input line, so that I can paste programs from the Windows computer into here. I can type interactively. You can read the video RAM, so you can get a screen dump from the Jupiter Ace onto the Windows machine. An ASCII screen dump. So this bus monitor has proved pretty helpful. And then finally, this last one is a speech synthesizer. So that's sort of always my first project with every one of my retro computers is a speech synthesizer. And I did it here as well. So we've got the SPO 256A-AL2, that's phonetic speech synthesizer. Very popular chip, was sold by Radio Shack for a long time. You can still get them on eBay. Be a little bit careful of counterfeiters. So it's very simple to interface with the bus. You've got some data bits. bytes. You just put them on a port. You can write the port and tell it to load into the Speet synthesizer, and it will speak the phoneme. To get your status back, you just read from a port, and you can read back whether the Speet synthesizer is busy. So you wait while it's busy, and when it frees up, you send out the next phoneme. So you're kind of in a polling loop. You could use interrupts. I chose not to use interrupts. I just did polling. And again, I've got one of my GAL 22V10D programmable logic devices, handles all of the various port addressing and such to assign this a port. Then you've got an op amp and a LM386 amplifier on here. A couple jacks, one for line out, one for speaker output amplified. And like I said, you can put all three of these. You know, you just stack them like so, and you can attach all three of them to the computer at once if you want, like that. Okay, let's try out the RAM expansion first. So this is actually very easy to test. If we do a 15384, and then let's do at u dot. This will print out what it thinks is the top of RAM, which should be 16K, 16384, on an unexpanded Jupiter Ace. So there we go. 16384 is in that location. Now if we power it down, take my expansion here, plug it in, and it looks no different at boot up, but if we do a 15384 U dot again, now it says 0. And the reason it says 0 is because the top of memory is now at 65536 instead of 16384, and I believe it just truncated that to a 16-bit integer. So it rolled over from 65536 is actually 0 if you hack off the upper bits. There we are, our memory expansion is working as it should. And this is important because all of those games and stuff that I showed earlier, they're not going to run on the standard memory. The standard memory is less than 1 kilobyte available for program space. Adding this, you get another 48K, so you get a total of 49K for program space, which is plenty. Now let's try out my Raspberry Pi add-on module. So I'm going to power down the computer again. Going to attach this one. We'll just piggyback it on there, like so. The Raspberry Pi I currently have, it has its own power supply. That way I can reboot the Jupiter Ace repeatedly. Okay, so here we are inside the terminal program on my Linux computer talking to the Raspberry Pi that is mounted on that extension board. So I'm going to show you how this works. And what this command here, the command is called supercmd for supervisor command. It's going to push a line, and the line it'll push is called vlist. And it'll push that into the input buffer and then tell the Jupiter Ace that a return was pressed. So I'm going to execute this command. And then you can see right there it has done a vlist on the screen. Now if I wanted to read the screen, I could do python 3 supercmd.py screen dump. And this is going to read the video memory off the Jupiter Ace and print it on my terminal. So I can see at my desk what it says. And there's our vlist. So let me also show you how I can push a whole file through that input buffer. So I'm going to do a push file -f. Let's do music.f. And there you can see it's pushing each string into the input buffer and then hitting return at the end of it. And then over here, let's do a push line -s. And we'll call this one, what was it called? Oops. Gotta remember my own command syntax. I use capital S. Okay, so that's the basics. It's also got some commands like peek, 1, 2, 3, 4. Let's just see what's in that address. Just reads a byte, so you can also do a poke. Oh, dash B56. There we go. So that's how you would poke a value. So I don't think that actually did anything because I think I actually poked it into ROM because I don't want to actually glitch the RAM. Now we can also load tape files. So tape files, we just blast them into memory. You saw me doing that a little bit earlier when I was playing the Tut Tut game. So this is how I did it here. I just went over here and I did this. And all of a sudden, Tut Tut will just show up in memory. Let me do a push line. Now, for some reason, I always have to do this twice. The first time will always generate an error, but the second time the command runs. Okay, now let's try out the speech synthesizer. So I've got that board here. I've got a speaker that's just a speaker in a wood box. We'll take and we'll plug it into the back here. Line up the connector right. There we go. And we'll turn it on. Now nothing special is going to happen yet. I need to load a program. So I did make this compatible with something called the Big Mouth speech synthesizer. And I found the Big Mouth online and I found a demo program for it. So I chose to use the same port numbers, the same chip. So their demo program will work with my board. So you're seeing here it's loading the demo program. It defines a bunch of phonemes. Phonemes are the unit of speech that a phonetic speech synthesizer uses. So for example, like the UH phoneme, it sounds like and it's the number 30. So it puts all of these words in the dictionary. This is another place where it's nice to have more than the standard 1 kilobyte of RAM. And then it generates one little demo here at the bottom called announce. And it will say, I am the Jupiter Ace computer, and it will call on these particular phonemes in order to say that. So if we go over here and we type announce.
I am the Jupiter Ace computer.
So anyway, phonetic speech synthesizer, you have to do the text-to-speech kind of in your head, and you had to translate, you know, the sentence into these phonemes. You can write a text-to-speech program, and I have written a text-to-speech program based on the Naval Research Labs algorithm. I've done that for many different computers. I don't know that I have a Z80 implementation of it yet, but it would be relatively easy to write text-to-speech. Takes a couple kilobytes of RAM maybe to implement that algorithm. And then you would have maybe a more convenient interface than this. Anyhow, that's it for my 3 little expansion boards that I built to try out this Jupiter Ace. I hope you enjoyed them. Okay, in conclusion, I hope you enjoyed seeing this Jupiter Ace video, seeing a little bit of Forth programming, some Forth games, and of course the expansion modules that I built to go along with this thing. So I will put up the Gerbers and the schematics and such for these additional modules in case you have a Jupiter Ace or a reproduction and you want to build any of these yourself. Thanks very much, and please do subscribe to my channel. Thank you for watching my video. Please visit my website at www.smbaker.com for more electronics projects and sandrail stuff. Bye.